Okay, welcome back. So today we will learn about semi-supervised learning. Is the third type of learning for this class. So before we learn about supervised and unsupervised, so for supervised learning, um, your data have label, right? So you know the correct answer for each of the data. For unsupervised data, all of your data do not have label, but you still want to find some structure inside those data. Today we have something in between, right? So what is semi-supervised learning? So semi-supervised learning um, is a way to combine small amount of label data. So you have the data with correct answer, but they are very small. You also have another set of data called unlabeled data. And this data, you don't have any information at all. So you want to combine them to make maybe some machine learning model, right? So if you look at the image at the start, on the top, right, is your label data, right? You only have two data points, one for black, one for white. So if you only use these two data points to create a classifier, you would get something along this line, right? You split the pen into white and black. But when you have more data, right? For example, you have this gray data. This gray data do not have label, so you do not know if it's white or if it's black. But having this information, maybe you can have a better, a more generalized classifier to also take advantage of this data point. So today we will learn how to incorporate the gray data point to our small label data. So the key point is that the label data is small and the unlabeled data is large, right? So you are looking at maybe like 1% of your data is labeled and then 99% of your data is unlabeled. So what inspired this type of learning? Um, so the label data is very nice because you actually know what is going on, and it's easier for the learning process, right? Because you can correct the model to change the outcome to match the ground truth. But acquiring label data is very uh, is very time consuming, right? Because you need to have people like as human to actually to actually like write down what type of the data it is. Like if you have, let's say you have like 10,000 image, you would have someone to actually write maybe a table like this image belong to this class, this image belong to this class, right? And if you have something like um, autonomous driving, right? Something like this image, what you need to do is like not only that you have to label, you have to actually mark the pixel, right? If it's a road, if it's a car, if it's a pedestrian, or if it's a tree or a building, right? So one snapshot, you will need to do all of this, right? And of course, humans do make mistake, and we want to reduce that mistake as much as we can, right? And if you think about labeling like this data, if you have like maybe you drive for 10 minutes and for 1 second, maybe you have like 24 frames. So you multiply that and that you have like just for 10 minutes of data, you need to have like a lot of images that you have to label. So for unlabeled data, it's very easy to obtain. If you have images, you can just download it from maybe like Shutterstock or just Google search, right? Like those are the images that you can search from the internet and you don't have to label them. So unlabeled data is more common, right? It's more common, and we want to use this large data to help our small set of labeled data. So we need to make some assumption to make the learning process easier. And this assumption, like we have like these three assumptions, most of the time, you should check this assumption before applying the semi-supervised learning. But sometimes people don't and just use like semi-supervised as is. And the results can be unstable if you do not check this condition before. And sometimes checking this condition require expertise on the dataset. So the first assumption is a continuity assumption. And this assumption says that data points are closer to each other tend to have the same label. Right? So this assumption is something you will see in KNN. Right? You would think that, well, if this data point is close to this one, maybe they share the same label. Right? And with just this condition, right, we can just use KNN. For every unlabeled data point you have, you perform KNN on the label data point, and which one is closer, well, you can assign the label that way. And this is one of the most common assumptions you can make. It's something that you have to check, right? So for this assumption to work, you need to provide the distance function, right? To be able to measure how close two data points are in your input space. The next assumption is called cluster assumption. And the cluster assumption says that the data can be divided into discrete cluster. So what do we mean by discrete cluster? So the data with the same label, should form some kind of a distribution in the input space that maybe have like some variant in one direction and then small variant in another direction. And point in the same cluster should share the same label. So this one up from the continuity, right? Continuity only look at pairwise, but this one look at the global structure of the dataset. So if you have the data point in here, even though it's closer to the blue, but it belongs to the green cluster, right? So if we can do that, then we can apply semi-supervised learning. So often enough, people would use the unsupervised learning, like for example, clustering technique. Right? Let's say you pick like 10 or 20 cluster and cluster all of the data point together, so label and unlabeled together, and check whether or not the cluster that you have the label data with the same label, right? So if the majority of the cluster, if the majority of the points in the same cluster share the same label, then this condition would be satisfied, right? So this one is easier to check. And the last one is manifold assumption, and this assumption is a very high level. So this assumption says that the data lie approximately on a manifold of much lower dimension than the input space. So what do I mean by that, right? So if you think of maybe your you have like a piece of paper, right? It's 2D, right? It's basically 2D. And then you plot the point onto the paper, right? So you have the 2D data. And when you crumble the paper, you will get a 3D, right? Because now the point are not in the same line, right? So basically you have the 3D data point, but the structure is actually 2D because the space in the 2D got distorted into a higher dimension, right? So this assumption says that you can reduce the dimension of the data set to a lower dimension, and the structure in the lower dimension actually can explain the data, right? So this allows us to define a distance and a density function on a manifold, right? This one is really hard to check because you do not know the transformation from a high dimension to a low dimension, right? You don't know what is the best way to transform. But if these two doesn't work, right? These two you check and it doesn't work, maybe you have to reduce the dimension of data into a lower dimension and then check again, right? And then check the first two conditions again. So that is the three main assumptions for semi-supervised learning to be able to work on your data set. So for the semi-supervised learning, we have three paradigms, three methods of doing it. The first method is called self-training. Um, Self-training, as the name suggests, is you train on your own data set and then you try to extend the label outward. We have the consistency regularization, and the consistency regularization does not train the data based on the label data, but try to make sure that the first assumption is still correct. And then we have a hybrid method, which is a little bit of both. So let's start with the cell training. So the key idea for a cell training is that, well, you have label data. So let's start with it, right? We start with a label data. What can we do with a label data? We can build a model, right? A classifier model. So we make a model for label data. And then the model that we have, we use it to predict the unlabeled data. And the prediction you have will be called pseudo label, right? So the pseudo label is the label of the unlabeled data that use a model from unlabeled data. And once you have pseudo label, you can train everything again, right? So you start with label data, you build a model, you use this model on the unlabeled data, you get more label, and then everything now is label. Like you have label and pseudo label. You can use them both, and then you can build the last model. You can repeat this process many times. Maybe you can pick the number of times that you want to build, or you can check whether or not the prediction do not change from run to run. Because if the prediction doesn't change, your pseudo label will keep the same label throughout. So that is the key idea. So what is the problem with this? Right. Now, the first problem that occurs is that your label data is very small, right? So when it is very small, you build a model from a small data set, you're not gonna get a very good model, right? A very good result. And when you have a not so good model, but then you apply for a large data, right? So you have uncertainty. You have like a lot of incorrect answer for a higher data, and now you combine both of them, right? The one with a very small set of accurate data, and a large set of inaccurate data. So if your data is inaccurate, then your model is not going to become a good model, right? So if you have a bad data, no matter how good your algorithm is, you are not going to get a very good model. So we have to not trust this pseudo label too much, right? Because it's something that come from your model that you still don't trust. So how can we improve this, right? To make sure that, well, we don't want to rely on the pseudo label too much, but we still want to use the model that we have from the label data. So we have something called a graphical method, right? So instead of creating a model and then just transfer it, right, to get a pseudo label for the rest of the data, we can model our dataset as a graph, right? In computer science, a graph consists of vertex and edge, right? So this dot here is the vertex, and then we have the edge, right? So edge is basically a connection between two vertices. And the weight, right? So this edge have a weight. Now this weight on the edge, it will represent the similarity between two data points, right? So it can be maybe Euclidean distance or maybe cosine similarity, right? So this is something that you have already done in the unsupervised learning, right? So we start with unsupervised learning. We don't use label yet. We have every data we create a graph, right? So when we create a graph, what we want to do is we want to assign the label, right? We want to assign a label. So, right, for example, if let's say I have positive and negative over here, right? If you want to assign a label for this point, what should it be? Should it be positive or should it be negative? Right? If I create the graph and then I have positive over there, negative over there, and then the rest is unlabeled, what should be the label of this point? Okay, someone say positive. Why do you think it is positive? So you look at the distance, maybe, right? The distance, right? So you say that, okay, this one is closer to positive than the negative. So, you should have the same label. So we want to use that intuition, but we have to write that intuition in mathematical formula, right? So for the computer to understand. So how can we write this intuition into the mathematical equation, right? So this is the equation. So how can we read equation? Okay. So this is something that we want to minimize. We have the summation over all ij. So I and j is the vertices. Basically, we look at a pair of the data, right? The weight ij is basically the distance, right? The distance of the data. And then yi minus yj. What is this? What is the yi minus yj? And then square. So you have positive and negative example, right? So you have a positive and negative, right? So you have +1 and -1 basically. If yi and yj are the same label, right? Have the same label, what is this going to be? 0, right? It's going to be 0. So if they have the same label, basically this term becomes 0, right? Becomes 0. But if it doesn't have the same label, what do you get? So you either get 1 minus 1 or -1 -1, right? So you get 4 basically, right? 2 square, you get 4. So if they're mismatched, right? For example, this pair, you get 4 times the weight of this one. So for every mismatch that you have for each pair, the weight will contribute to your error function, basically. And we want this to be small, right? We want this to be small. And when we want this to be small, which W we want to pay? Do we want to pay high W or low W? We want to pay low W, right? So for the W that are high, we want the label to be the same, right? So if the 2 points are similar, the W, the weight, should go up, right? It should be very high, right? If it's similar. So if it's high, you want to assign yi and yj to be the same label, so that the term for this pair becomes 0, right? So you don't have to pay the weight. But when the data points are too far away, right? Too far away, right? The weight will be very low. And it's okay for you to assign a different label because what you contribute to the error function is a very small, right? Compared to the one that are higher. And this is something we call energy minimization problem, right? So you measure the energy between two vertex. Right? So you want to find the yi, right? You want to find the best yi for every vertex, right? You want to find the labeling such that this expression is minimized. And well, for this one, right, it means that we can pick yi and yj freely. So this expression work on totally unlabeled data, right? Because the yi and yj are variable, you can change them. So this equation is work for unlabeled data, right? So if you don't have the label, you can use energy minimization to get the result. But we have a small set of label data. So we have to have some constraint for those, right? And so we add this constraint, right? So we add this constraint. So the left side is the same, right? The left side is the same. And then we add another term, right? Plus lambda times the sum of the function between yk and y prime k. So what does it mean? Right? It means that we want to force the label. So this yk is basically your variable, and the y prime k is your label, the true label, right? So you want this to be, so basically you want to force the label to be the one that you already know the answer, but sometimes forcing it is actually very hard for the optimization to work. So basically the data that is already have a label will have a pseudo label of its own. And this equation said that, well, you have the correct label, you have the pseudo label, and if they are different, you would add some penalty to it. Right? So you don't actually force that, okay, this yk has to be 1 because our label data said that this data is 1. We don't do that. Everything is a pseudo label, but if that data have the true label, it's going to contribute to another term, another way, another error. If the pseudo label is different from the actual label, you add some penalty, right? And then you have this lambda to control how strict you are by forcing the label, right? So if lambda is maybe like 100 or 1,000, it may be that you want the energy minimization to strictly follow the true label. But if lambda is small, maybe the true label, you don't touch them 100%. There are room that they can change the label throughout the training process. So that is the how you would come up with an equation to capture this kind of intuition, right? So you should be able to translate like your human language into mathematical language, and at the same time you should be able to read the mathematical language and then understand the original intuition of why we write it this way. So that is the energy minimization problem. Now, when we create a graph, right? When we create a graph, you don't want the graph to be very dense. What I mean by very dense means that the graph have a lot of edges. And when you have a lot of edges, when you want to minimize each pair, it's going to be very difficult. So what we can do is we want to make the graph a little more lightweight. And when we want to do it that way, we will use the k nearest neighbor graph, right? So instead of having, so for example, if you have like 1,000 data points, right? So you have 1,000 data points, and if you create every pair of the data point, you would have something like 1 million edges, right? 1 million edges. And to compute the weight for 1 million edges is going to take a lot of time. So therefore, you use the k nearest neighbor. So one point will have an edge into k neighbor, right? So instead of like all pair, you would have like 1,000 times k, right? 1,000 times k. Like if you pick k to be 5, then you will have 5,000 edges. And this will help with the computational cost. So when we have this sparse graph, what can we do next, right? We can actually, well, instead of doing energy minimization, we can do a stepping stone approach, right? So we have this sparse graph, we have this data point, right? Maybe we have negative example here, and then we have positive example here. Now, if you were to use, because when we create a sparse graph, right, is it possible that For example, you have this point here. How would you assign the label? Right? Because the neighbor is also a label, right? So you have to go through many steps until you reach a data point that have a label. And what we can do is we can do a random walk. So what do we mean by random walk? So you start at one point, right? You start at one point. This one point, it will have edges to its neighborhood. And we are going to use that weight to compute the probability of, going into that the next data point, right? So let's say if the distance, actually the weight, like the similarity, let's say this similarity is maybe 1.7 and this similarity is maybe 0.5. So when you take a random walk, right, you take a random step to this point more often than the point with lower weight, right? So you use the weight to define the probability of going into the next point. And you keep doing this, right? You keep doing random walk, right? You start with one point, you look at the neighborhood, you just take a random guess, but not everyone have equal weight. The one that are closer to you will have higher weight of you going there. And then you repeat this process until you find the label, right? So when you find the data with the label, that label will be transferred to your starting point. So if we start with the yellow, right? We have the yellow dot over here, right? We have the blue random walk, right? Maybe it walked down the path and then maybe we come back into the zero. And then we have the green, right? That can like dabbling around and then hit once. And then you can also have a random walk with the purple line. And depending on your luck, you can assign the yellow point with 0 or 1, right? Based on which node it actually reached at the end. And to compute the random the random walk efficiently, we are going to use the matrix, right? So the matrix, you will have the sparse matrix, and you have the weight, right, for every I and j, and the probability of going from I to j, right? Basically, you multiply the weight from I to something else, and then something else to j, I to something else, and then something else to j. So basically, you look at all the possible way from I to reach j, and then you sum up the probability. So once you compute the probability of ij, you can look at perhaps what j have the highest probability, right? If you start with I and I is unlabeled, you will look at all the j that are labeled and then take the one with higher probability. So this method is called a construction method. A construction means that you don't do any optimization. You construct um, your cost and then you try to reach the conclusion with the cost that you start with. So this is the random walk method. So after the random walk method, we can also use a mixture model. We learned the mixture model previously. So the mixture model that we learned, basically we have a small cluster, like multiple cluster. So we can do the same, right? We use the mixture model to create multiple clusters, and the data that belong to the small cluster will have the same label. And your assumption would be that when you pick the number of model, you pick the number of cluster, you want to make sure that every cluster have at least one label data, right? Because if you come up with a cluster that have unlabeled data, then you cannot assign anything. But if you have the label data in the cluster, then you can do some kind of like a majority vote, right? If you have more positive label, then the entire group would be positive, and vice versa. So that is the mixture model. And then we come back to the pseudo label, right? So we talk about pseudo label is a label that you get from predicting the unlabeled data using a model from unlabeled data. And we talk about the pseudo label being not accurate, right? Inaccurate. And so we have an approach, right? We have an approach that, well, if you think that the pseudo label is inaccurate, perhaps you can use weight to control how much the error from the real label and the store label, right? So originally we have label image, let's say label image, and then you create a model, and then you have the prediction, and then you have label, and then you can use the cross entropy loss to update the model, right? So you finish this part. And then when you have a labeled image, right? Now, unlabeled image, you pass to the model, right? You pass to the model, and then you also use the cross entropy loss the same way. But instead of just adding them, right? So we have the loss for the labeled data, and then we have the loss of the unlabeled data. We will introduce this weight, right? Alpha. And notice it's not alpha, just alpha. It's alpha with T subscription. So what does it mean by having the T subscription? It means that this alpha is not constant for the entire training process. And this alpha is going to change over time. So intuitively, when you start from the first run, right? When you start from the first run, your label data, the loss of your label data would be accurate. And the loss of the unlabeled data would be very inaccurate. And so because this one is inaccurate, at the beginning, you would set this to be very low, right? So at the start, maybe the first 100 epoch, you set this to be very close to zero, right? So this one may be like 0.01 or something like that. And then after you train for a bit, you start to gain a confidence on the unlabeled data. So when you have more confidence, now you can increase, right? You can increase the weight of the unlabeled data. And then at some point, you will stop. So that is the learning weight for semi-supervised learning, right? So this weight actually capture the intuition that, well, at the beginning, we don't trust the pseudo label, but later on, when we have a stronger model, then we can trust more, so we can maybe increase the weight. So as you can see, right? So if we use 1 to be around here, so a learning weight of 1 means that we have equal, right? We have equal emphasis on both label and unlabeled. But with this graph, we actually put more weight on the unlabeled. Why is that? Why are we not stop at 1? Why we go up to 2 to 3? What is the reason for having higher weight than 1 at the later step? I'm not gonna tell you the answer now, but maybe someday. And then later on, so we use this type of learning for a while, right? When we have the weight between the label and unlabeled. And then in 2019, we start to playing with the model now, right? So before we only have one model, right? We only have one model. And you train the same model over and over. But the loss function change over time, depending on the learning weight. Now we have 2 models. So we have the model called teacher, and then we have a model called student. So as the name suggests, right, the teacher would be like more accurate than the student, generally. So the teacher, right, the teacher is basically the original model, right? It's the model that only use the label data, right? So the teacher is using the correct label. And then we use this teacher to create a pseudo label, right? Create a pseudo label for unlabeled data. And then we will train the student based on both data. However, we will use both label and unlabeled image, but we also add the noise. We also add random augmentation, and then you train the student. And after you train the student for that iteration, the student become a teacher. So this become a teacher, and then this teacher will train with the label image using the true label, like to become the next generation teacher, and then you repeat the same process, right? So when you start the training, the teacher will have random weight, right, for the initialization, right? And then you train only use labeled image. But after you get the student, when the student become a teacher, it means that the teacher, the initialization weight of the teacher is from the student. So you're not gonna start with a random weight again. You start with a weight from the student, and then you basically retrain it, right? You retrain the student using the label data so that it become the next gen teacher, right? And then you keep repeating the same process over and over until maybe you can pick the number of iteration, or you can have a different termination condition. So that is the self-learning, right? So the self-learning, you would use a labeled image plus pseudo label, and then you can play around with the learning weight, or you play around with the model, right? So for this one, when you train the student, you can still use uh, the different learning weight as well. You can use that, or you can just pick the alpha to be one, your choice. Right. So that is the self-learning paradigm. The next paradigm is consistency regularization. So the key idea is actually from the first assumption that data points that are close to each other tend to have the same label. But for here, the data and the data plus noise should have the same label. The noise should not have the impact on the label. So if you have one image, maybe you flip it, or maybe you change the lighting condition, and when you put through the model, you should have the same label, basically. Okay, so that is the key idea. So how should we use this idea to perform the semi-supervised learning? So in 2017, we have a pi model. Now, a pi model used two random augmentation data. And then we use a model with dropout. We will learn a little bit about the dropout to predict intent. And we actually use a different loss function between the labeled data and unlabeled data. So each image, right? Each image, it doesn't mean that this one can be labeled or unlabeled. Each image will go to augmentation, right? Will go to augmentation. And the augmentation, you will learn the model, right? We use it to learn a model. And this model should produce a prediction. And depending on which type of image it is, we are going to use a different loss function. So for label image, we use cross entropy. Why do we use cross entropy loss? Because we know the answer. We know the correct answer. So if we know the correct answer, you want the prediction to have the similar probability distribution to the correct answer. That's why we use cross entropy loss. But for unlabeled data, we don't have the correct answer, right? But because we augment the image, right? We have, for one image, maybe we augment like 10 augmented image, and then pass through the same model, and then each image will generate a different distribution, and then we can use the square difference to compute the loss, right? So basically, for label image, whatever you get, you compare it with the ground truth. For unlabeled, you will try multiple augmentation, like you try to flip image, you try to rotate image in like different angle, and each one of them will produce the different answer distribution, and you calculate that, I don't know what is the true distribution for this one, but every one that you get, it should be the same because it's basically the same image. So we could use this to use the square difference, right? Because we have the two different answers, and we want this square difference to be very small, right? And then you have these two weights, you combine it into the final loss function. So in this model, you can see there is no pseudo label, right? You unlabeled data, you don't assign a label, and you never assign the label. Like the result you get, you just compare the result with noise, with the data plus noise. So that is a very clever way to utilize the unlabeled data, right? Because you don't know the answer, but if you augment the data, your answer should be similar. So what is the dropout, right? So in neural network, right, we have a layer, right? So this the maybe input layer, maybe these two are the hidden layer, and then we have the output layer, right? So in a neural network, the dropout mean that during the training process, when you do the back propagation algorithm, some node will be inactive, right? Some node will be inactive, and this will help with avoid overfitting. Like if you have a lot of information, you want to store all the information, right? So this is the dropout. So basically, some node it just becomes zero, right? It just doesn't send out any signal. Doesn't matter what input it come to, and each training step, you pick a different node to be inactive, right? It doesn't have to be the same node. So that is the model with the dropout. And then we have an upgrade from Pi model called a temporal assembling. This one uses exponential moving average for the prediction. So what do I mean by exponential moving average? So have you heard of the EMA before? So for the moving average, right? For the moving average, so basically, let's say you have like the data with time, something like this. When you compute the moving average, you pick a small window, and then you calculate the average for that window, right? And then when you go over time, you only look at the small window, the same size of window, and then you calculate the average. So this is the moving average. Now, for the exponential moving average, you need the same thing with the moving average, except that the weight when you do, so normally when you have average, right, you would have the summation of x over n, right, basically, right? You basically average everything. But for exponential moving average, each x you will have some weight, and this weight will follow the exponential decay. So the data that are old will have small weight. The data that are new will have higher weight. And we can use this for the unlabeled data, right? So for the labeled data, we use the same thing, right? We augment it, we compare it with the label using cost entropy loss. So that is the same. Now, the difference is that for the unlabeled data, right, we augment it, we get the prediction, and instead of this prediction comparing with the other prediction in the same iteration, we will compare it with the moving average of the prediction in the past, right? Because we are doing it multiple times. So this one will be the average of your previous iteration, right? So in the first iteration, no, you would not have this, so you can use just the square difference. But for the next iteration, you have this prediction from the previous iteration, so we save it. And then you can compare it with your saved prediction. And after you save it, you just combine this with your saved one. For the next iteration, that you use your average that you save. So this one have a sense of evolution across the iteration, right? So not just look at the current iteration, but the weight, right? The prediction, the property of the prediction should not change too much. Right? It should change gradually, but within like the immediate from the current iteration to the next, it should not change too much. Right? So basically we are not comparing with the same run, but we compare it with the previous run. So that is the temporal assembling. Right? So the word temporal will mean time. Right? So you use the past prediction to dictate the future prediction. So a little bit about EMA. There are many weights for the moving average, and we have the exponential moving wedge and a straight moving average. So the straight moving average would be this black, right? So basically every data point in the same window will have the same weight. But exponential, you have this red and blue. So you can have the red with a slow exponential, and the blue would be a steep exponential. And the reason being that we want to use the exponential weight is that the recent the model is, the higher the weight become. Because at the beginning, our model is very inaccurate. But later on, the model is more accurate. So we trust the result from the recent one more, but we don't want to throw away what we have done before. So that's why we have to combine them, but we combine them with smaller weight from the past. And then we have a method called mean teacher. So remember that we have the teacher and student model, right? So we have teacher trained on the label data, and then the student trained on the label and pseudo label. So now we want to use EMA. We still don't want to use EMA, but we don't use EMA on the prediction. We use EMA on the weight of the model. So normally the teacher and student would have the same neural network structure, right? And for the teacher, right? So the teacher is the EMA of the weight of the student model. So at every iteration, the model that we get will always be student, right? Will always be student. So we train the student, right? With both label and unlabeled. And if we use the label data, we compare it with the ground truth. So that is the same. But if you have the unlabeled data, instead of comparing it with the student of the previous iteration, we will compare it with the result from the teacher. And the teacher is the EMA of the student, right? So in first iteration, you have student 1, right? The second iteration, you have student 2. And while you want to train the student 2, the teacher is basically the student 1, right? So we have the prediction from student 1, the prediction from student 2, and then you use the square difference to compare the prediction, right? So the student and the teacher should have the same prediction. And when you want to train the student 3, at iteration 3, the teacher become a combination of 1 and 2. And you want to compare the result from the third student and the teacher is the EMA of the previous student. So EMA here means that when you have this model, right? For example, if let's say we have this to be like a student, right? The teacher would just copy weight, right? We will copy weight from the student, and then when we have a new student, right? The teacher will have the same weight plus the weight times the new student, right? So the new student will contribute a little bit more to the teacher. So the teacher is an accumulation of the student, right? So this is called a mean teacher. So mean here mean average, not by like being mean, literally. And then we have a different approach, a little bit different approach from Miyoto. This one is called virtual adversarial training. So virtual adversarial training is basically get an expression from GAN, right? It's a generalized adversary network. And what happened is that, well, for the label data, we compare it with the ground truth, right? So every method use the same concept, right? If you have the label, then you just compare with the label. If you don't have the label, it's gonna try to create adversarial example. So not just augmented, but adversarial. So adversarial means that you want to try to add some noise to the image, or maybe change the color, but for human perspective, it's the same image. But for the model, it should produce a different result. So for here, when we have the adversarial example, right, you pass through the same model, you have a different prediction, and then you use the KL divergence loss to compute the difference between two of them. So the KL divergence will make sure that the distribution of the prediction between the two should be the same. So KL divergence is the stronger loss function than the square difference, right? Because we want, basically we try to create an image that will fool the model to get the wrong prediction. And we also want to learn to not be affected by the adversarial example. So the question becomes, how do we create adversarial example? Right? For augmentation, it's very straightforward, right? You can rotate image, you can change the lighting condition. But for adversarial image, you want to create image such that the model would give a totally different prediction, right? You try to fool the model. How can you create an image that to try to fool the model in the first place? And there are many ways to try to create. The most simple one is you just add noise, add a lot of noise. Right? For example, you have the truck image, right? You add this type of noise, like just random noise, and then you will get maybe the same truck, but maybe the color change slightly, right? So this is the adversarial example. Another strategy you would try is rotation, right? So rotation, maybe it works, maybe it doesn't, but rotating might actually be difficult for a computer, right? Because if you look at the number in the 2D, the structure change a lot. And the more advanced one, you use the photographer wise. So basically, maybe you have the same snack, but you take the close-up shot, and then you take a far-away shot, right? So that is the advanced version of the adversarial. They should give you the same label that is not a hot dog, but if you take it far away, maybe you take one pack from the box, and then you take it far away, maybe it just look like a hot dog, right? Because the shape is like a hot dog. So that is a way that you can fool the model. So KL divergence is actually is a measurement to when you have a property model, it will measure how far one property model is from the other. And when you want to minimize the KL divergence, you want the property to be as close as possible. So instead of create adversarial image, right? You can use auto augmentation, right? Basically, this augmentation instead of cropping by hand, right? So in the previous algorithm, like you do it by hand, right? You just pick how much you rotate and so on, right? So that have a human intervention, right? You pick the noise, right? You are the one who pick the noise, and then you add them. Now, for auto augmentation, we want to create something that can be done like automatically, right? And if we can do auto augmentation, we can replace this auto augmentation with adversarial example or stochastic um, augmentation. How can we do augmentation automatically? So we can create a policy, right? Augmentation policy. And one of the successful policy is from ImageNet. Basically, it will have like multiple policy. Um, and then from the original, right, it's gonna try to create a different augmentation. So each augmentation is not just only rotation, but also have a different lighting condition. So in the paper by ImageNet, when they have the auto augmentation, they have a way to search, right, for the one that would contribute to the dataset the best. And a lot of policy from the ImageNet actually have is a color-based transformation. Right? For example, if you take a photo at the night, it will try to augment it so that it look like you take a photo in the morning. So that is the auto augmentation. I'm not going to go into the detail. There are like a long list of the literature review about the auto augmentation. So we learned the self-training, right? So the self-training have pseudo label. For consistency regularization, we focus on augmented data, right? Augmented unlabeled data should have the same label as the original unlabeled data. So when we want to combine both, right, how can we make sure that we actually take advantages from both methods, right? Because combining doesn't mean you can just stick two algorithms together, because sometimes they like cancel each other out. So we need to find a way to combine them. And one of the most common is called mix match. It's the most common hybrid algorithm. And the step, right, you start with self-train, right? So basically in the first step, you use the self-training paradigm. So what is the self-training paradigm? You train label image, you get a model. You use model on unlabeled data, and then you get pseudo label, right? So once you get pseudo label, now you can move on to the step 2. Now, the pseudo label for mismatch is not just original image passed to the model, but they actually augment an image. They get the prediction. They take the average of all the prediction of the augmented data, and then you do the temperature sharpening to make sure that one is more prominent than the other, and then you get this pseudo label, right? So the label, normally you would have 1 and 0, right? 1 and 0. For pseudo label, you might have like 0.9 and 0.1, right? So pseudo label doesn't mean that it's a label, but it's a probability of like having one label compared to the other. So that is the first step, self-train. So after the self-train, right, what we do is we do data shuffle. So what is the data shuffle? Basically, we have N augmented label image, and then we have M augmented unlabeled image. So basically, we augment both label and unlabeled, and then we combine them, right? We shuffle them, and then we split into the first N image and then the remaining M image, right? So we start with basically one set of label, one set of unlabel. Then you mix, and then you get the two group. But this group will be a mix between label and unlabel. So when you mix, the next one is you apply the mix up, right? You apply the mix up to your label, right? To your label. And you will get the label group, right? You have the label group. And this label group, you will compute the mix up label, right? So normally this is like cat, dog, right? Your augmented label is going to have like 0, 1, right? Cat, dog. But this one may not have 0, 1 because some of them will have a pseudo label. And then you try to take, perhaps you try to take like the average of all of the label. So this entire group, you have this label. And then you apply the mix up for the unlabel as well. And then you compute the mix up label. And once you have label group and unlabeled group, you can train the model using consistency regularization. So in the label group, we trust that everything is accurate. And your mix up label become the true label. So when you train the model on the label group, you use cost entropy loss, right? Because you trust that this is the correct answer. And then for unlabeled group, right? For each image in the unlabeled group, we pass to the model, we get the prediction, and this prediction will compare with the mix up label of the unlabeled group. And we can use maybe MSE, mean square error, or square difference loss. It's the same thing. And then you combine the loss function, right? So this one is from the consistency regularization. Right, and that is pretty much how you would combine both methods, right? So just a quick recap, right? You start with self-train. You have the model from label. You get the pseudo label using that model. And then you mix up the label. So basically you have one original label image, right? And then you augment it n times to get n of the same cat, but like you augment it n times, right? And then you have the unlabeled image for one label image, for one unlabeled image, you augment it m times, right? And then you combine, and then you shuffle, and then you split into two groups. And the first group is basically treated as the same as this one, right? The one that you are confident. And then the bottom group would treat as not so much confident. And then once you have that, you still have to compute the mix up label. You can do the average, or you can use like different type of averaging. And then at the final step, you use the consistency regularization algorithm. So for the label, you compare with the mix up label with, no, you think that would be the graph truth. And for a label group, you compare it with the mix up label of the entire group. So that is semi-supervised learning. right? So you learn many ways of transferring the label from the label data into unlabeled. There's no like the best method. Each method would follow different assumption, and I show you the pre-assumption at the beginning. So make sure that after you check one of the assumption if it hold before you apply uh, semi-supervised learning, right? So any question? Um, I think you might probably see semi-supervised learning a lot. Maybe if you want to like in your project, unless you use like benchmark database, because the benchmark database will have like all the label. But if you have to take the data of your own, maybe you don't have label, and then you can try use semi-supervised learning method to come up with the label. In some cases, for the benchmark dataset, so each benchmark dataset will have to publish a paper for that dataset, right? And some of the benchmark dataset actually use semi-supervised learning because the cost of labeling is very high. So they use semi-supervised to help with the initial labeling, and then they will have a human to actually cross-check all of the result, right? So if you go back to uh, this image at the beginning, right? When you have to label basically every pixel on the image, right? For human to have to like pick the pixel is probably very hard. So they will have uh, the semi-supervised learning method to actually segment out each part and then have human pick, okay, this part would be the car, this part would be the road, right? So um, many of the benchmark data set would combine both like human work with the semi-supervised learning. Okay. Um, so we're gonna take about like 10-minute breaks, and then we'll come back. I will show you some coding for the semi-supervised learning as well as CNN, because we haven't seen CNN since we learned it from the neural network. So I will be back at like 10:35. Okay. So we are back. I will start with introducing the CNN first. Um, Today we are going to use the CNN via PyTorch, which is a library for neural network. Because last time we used sklearn, right, for the neural network. We'll use PyTorch this time. So we need to import some library from PyTorch. So you start with import torch, that would be the main library. And then we want to import the torch NN as the neural network and also the functional. So basically the function that we will use inside the uh, the neural network. And then we are going to import, um, we will import later as we go. So first we have to load the dataset, and we are going to use the Cipher10 dataset. And this Cipher10 dataset is from the Torch Vision. So it's from the computer vision dataset. It will be an image. And so we import two library. So the Torch Vision will have the data, and we have the transform. So this transform is basically an augmentation, right? Basically, it will do the flip image for you and so on and so forth, right? So you will start with you getting the data. So we have the torch vision dot dataset and then dot cipher10. That will be the cipher10 data. And inside, you would have to specify a lot of parameters, right? You have the root, like that would be the path of the cipher inside the torch dataset. And you want to download the train, right? And then you want to assign the transformation. So right now, the transformation that we use is from to tensor. So basically, whatever image they have, it will convert into the tensor format for you. But if you want to have your own augmentation, you can specify your own transform as well, right? For example, you can have the transform, and then you can compose them. So you have transform dot uh, compose, and inside here is the array, is the list of the augmentation method that you want to use. Now, for image, for the start, you would have the two tensor first. Basically, you convert the image into the tensor format, and then you would want to normalize the image to have the mean, right? So this will uh, like normalize image to have zero mean, right? Because image, typically you have like from 0 to 255, right, for each of the pixel value, and then you want to make sure that the average of the image become gray. So that is the transformation, and then you can put in your own transformation here. So that is the data download part. And then, so this would be your train data, and then your test data would be, you use the similar one, but you have the train to be false. So if the train to be false, you get the test data. And now we have our data, right? We can build the CNN model, right? So to build a CNN model, you have to create a class. And a class, for example, my CNN. So basically my CNN class, and the class have to extend the NN module, right? So this is the base class for all the neural network that we import earlier as NN. So we use nn.module, right? So this will be your class for like all the module. In this class, you have to write two functions. The first function is the initialize function. So you have two underscore in it and then two underscore, and then you have self. So the initialization, you will start with super. So super means that you will use whatever the base class. So the base class is the NN module. So the base class will also have its own initialize function. So basically we override that function, but we still use whatever they have at the beginning, right? So we use super in this case, right? You use the init from the super class. And now you can start building your neural network, right? For the CNN, you start with convolution layer, right? Maybe like 2 or 3 convolution layer, and then followed by the fully connected layer, right? So we start. So let's say we start with self dot the convolution layer 1, right? So we have nn dot convolution network 2D, and then you can specify the size. So the size, you can specify what is the input number of channel. So uh, your first convolution network, the the filter should have 3 channel, right? So it should have 3 channel, and then you specify the width and the height of the filter. So let's say 32. So it's 32 by 32 by 3 filter. And then you specify the kernel size, right? You can also specify the padding as well. So the padding is the step that the conversion will use. So that is the first layer. And then we can have the second layer. So make sure that in the second layer, the output of the first layer should match the input of the second layer. So it will have 32 channel because the first layer you have 32 filter. So it should have the same number. And then you have maybe 64 by 64 and then the same. And then maybe the third layer, you will go up to 128. And once you have all your convolution layer done, you will use the max pooling, right? So you have the max pooling here, like cell.pool equal to max pooling, the 2 dimension. And max pooling is going to give you the 2 by 2 image, and then you will finish off with the fully connected layer. So FC1 equal to the linear. So this linear will have 128 by 4 by 4, right? And then your output layer should be maybe 512. And then your final FC2, you have the linear and then 10. So this 10 here, 10 is the number of label, right? So for our data set, right, we use cipher 10. So there are 10 classes. So it's basically the number of classes in your data, right? So it's basically this will be your output. So this CNN will give you 10 number, and each number will correspond to each class in the model. So that is the initialization, right? So you basically define each layer in CNN. So once you define the layer, right, you have to tell them, right? So basically, you create this layer, but you haven't joined them yet. So the next function that you have to write is the call forward. And the function forward is basically tell the CNN how each layer is connected, right? So we have self and then X. So the forward X here, right? So X here is the data, X is the data. So when the data come into the network, right? What do you start with, right? You start with inside, you pass X to your first convolutional layer. After that, you have the rectified linear unit as the activation function, right? You have the activation function, and then you do the pooling, and then you get the new X, right? So basically, this is the output of the first CNN layer, right? And then you do the same for the 3T layer. So after we have this one, we can say x dot view minus 1, right? 128 times 4 times 4. So basically, you flatten the output of the last CNN layer. Right? So whatever it's gonna have the 2D image, right? Because it's the convolution network. So it's gonna switch the 2D into one line, right? And minus 1 here means that you flatten into just one dimension. And when you have these dimensions, right? So you have from here, you have 128, right? So you have 128, so we have 128, but then you have this pool, 2 by 2, so you times 4 times 4. And then you pass through the output into the fully connected layer, right? Followed by the activation function. So every time you pass through the layer, right, either to be the convolution layer or the fully connected layer, you have to have the activation function, right? And then at the end, for the final layer, you don't have the activation function because you want to get the result. So the result would be from the output of the last fully connected layer. So that is how you write CNN in PyTorch, right? You have two functions. You have the initialize function is basically describe each layer, and then you have the forward function will tell you when the X come in, what is the output, right? And then you have to write out the entire function for it. So compared to sklearn, you actually have to code a lot. But because of this, you can actually do a lot of customization, right? You can switch around, you can specify, maybe you change, maybe you want to use the rectified linear for the first layer, but the second layer you can use like something else, right? For example, what do we have? What do we have for PyTorch function? So you have the, man, what is it? It's not functional. Okay, it's functional. So it's functional. You have the linear function. Where is activation function? So you have, okay, so we have the nonlinear activation function, right? We have the redo normally. You can also have the hard hyperbolic tan as well. And then you have like different type of rectified linear, right? You can also use the log sigmoid, right? For example, if I want to use log sigmoid here, I can also do that here, right? You can do a lot of customization with this. So we now define the class, right? So we already defined the class, but when you define a class, it's just a definition, right? You haven't created the model yet, so you have to create a model. So we can say the model equal to my CNN, right? And then uh, so basically when you create the model, you want to tell like do you want to use CUDA as the basically you can pick between the CPU or GPU, right, to run the model on. For image, it's better to use the GPU. So I'm pretty sure if my oops, my runtime, I should use GPU, right? So I change. You can pick the GPU. So maybe a 100 GPU. And when I use GPU, I can use CUDA, right? And then I can maybe try to beat the model. So let's run this one first and to see what it print out. So we load the test and test data. We define the model for the CNN, and then we want to print out. So it's gonna take a little bit of time, about 170 megabytes. So when you print out the model, right, it's gonna tell you each of the network of each of the layer of what you have. So okay, so we have the layer. Now we want to train, right? We want to uh, train my CNN on the cipher data. So we define the model. We also have to define the criteria. So the criteria is basically what loss do you want to use. We can use the cross entropy loss. So what is the cross entropy loss? It's basically the loss that you compare the two distribution. And this is very common when you have the multi-class classification. You would use the cross entropy loss because you have multiple class. So basically you have the distribution over each of the class. And then you can specify the optimizer, basically how you want to optimize the weight inside your CNN. So the suggestion here, they use SGD, but we can actually use Adam, right? We can use Adam. It's the most common one. And then you pick the model parameter, and then you have the starting learning rate, right? So you can also play around with the learning rate for the start. So once we have the criteria and optimizer, we can start the training. So we have to decide how many epoch we have to run. So we say num epoch, maybe 20 iteration, 20 epoch. And then maybe we have, we store some number, for example, 10 loss, and then maybe we have 10 losses. We have the train accuracy, and then the test accuracy, right? So we want to basically plot the loss function over each epoch, right? That will tell you whether or not how well the model converts to the current model. So once we have this, right, we can start looping for each model. So for epoch in range of the num epoch, right, for each epoch. So for each epoch, what we have to do, right? So we have to first of all tell the model that we want to train. So this one will tell the model that we are in the training mode, right? So when the model is in training mode, the weight can be adjusted. So we have the train and the test loss, right? So we have the loss function. So right now we only look at the train, right? Because we haven't do the test yet. So we only have the train loss, train accuracy, and perhaps epoch loss, maybe. And then you have the triple zero. So we have to load each data, right? So right now we only load the data here, right? So we have to loop each image, right? So what we do is we for maybe we have the I and D in enumerate all the training data, right? And then we should have input and the label for each image, right? So equal to data and the zero, and I want to use CUDA so that I can train it on GPU. So I have the train and test. I have input and label. The next thing I do is I have to set the optimizer to zero gradient, right? So after I set the optimizer to the zero gradient, I do the prediction, right? So we have the output equal to the model input, right? So for each input, I will have the output. And this output is basically a 10 number, right? Each number corresponds to each class. So we have the output, and then we compute the loss of that output, right? So the loss function will be your criterion. It's basically the cost entropy loss between this input, this output with the true label, right? And then you do the loss backward. So when you do the loss backward, it's basically tell the model to update, right? It's gonna compute the update backward, right? And then you do the optimizer dot step. So it will be the next step of the optimizer. And then we have the 10 loss to be the loss plus item. So basically it will have so this will be the loss value. And then this one is you have your hard prediction, right? So output the data and then you take the maximum. So basically you take the one that have the maximum probability from the output, and then will be your prediction. And once you have the prediction, you can add it to the train accuracy, right? Because accuracy only compare whether or not you get it right or wrong. But the loss is basically the loss function, the cost entropy loss, right? And then the epoch loss would be the same and the train loss. And then after you finish with all the image, right, you append the loss divided by the number of the training. So it's the average loss, right? So for the 10 losses and the 10 accuracy, you add up and then you divide, right? So that is the normal calculation. So after this step, right? So after this step, we can also do evaluation, right? So after one epoch, you go to all of the images, you compute the loss, and then you update the model. So these two are basically update model weight. Okay. And now we want to um, evaluate. So we say model.eval. So this will tell the model that we want to evaluate. Do not change parameter weight, right? So if you don't tell it to be evaluation mode, when you put it into the test data, it's going to update the weight. So make sure that you tell that it's evaluation mode. So once you have the evaluation mode, right, you have the test accuracy and then the test loss, and then with torch no gradient. So before we use, you start with the zero gradient, but because we want to just test the model, we will not use any gradient because we don't update anything, so we don't use gradient. So with torch no gradient, you also enumerate the data set, right? So this one is the same as the above, right? But it's for the test data now. So when we have the input, the label, and then we use the same procedure, right? So the output would be the output from the model. Your loss would be comparing the probability distribution of the output and the probability distribution of the labels. And then for the test accuracy, you take the maximum. So it's become the hard prediction. And then you check if it's the same, then you sum up, and then you add it. And then you have the you append it into your array of the 10 losses so that you can plot it later. And before we finish the loop, we want to print out some information, right? So we want to print out which epoch do we have, right? So epoch number, whatever, what is the trend loss, what is the accuracy loss, what is the test loss, and so on, right? And this one I have to, so actually, hold on, let me set it to F. So we have epoch, right? So epoch plus 1, we will complete auto for, okay, so it's, we auto complete for me, nice. Okay, so we have, can I enter? No, I cannot enter. Okay, so it just print out the information. And then outside the loop, sometimes you want to print out the training complete. So you know that everything is complete. Right, so we can try to run. Let's see. So in attribute has no CUDA. So basically there's no CUDA here. So maybe I have to activate CUDA first. Um, so mostly I have to activate CUDA first. So I gonna to so I want to activate CUDA. So I would have my device equal to torch dot device, and if it's CUDA 0, if there's CUDA is available, otherwise CPU, right? So let's see. So we have CUDA, all right? So we have CUDA. And so because we have CUDA, I'm going to copy it to here. so that our model actually use CUDA. So instead of .CUDA, here I'm going to use tool and then device. Just to make sure that I actually use CUDA. And then if I do it here, so this one input is no longer CUDA. It's going to be to device and then to device, I think. And this one also. In object have name too. So maybe, so I get input from the data 0 and data 1. So if in input, can I just use this one? Let's see. So expect all the tensor to be the same device. So we have to find a way to convert the input into the same device. Let's see. So I cannot use data.toDevice, I guess, because it's already into ins. Right? Because if I use toDevice here, it's gonna tell me the answer. So let's see. Can Gemini help me? So the change that it suggests, so move the label to device. So how can I move my to device? So move tensor device am at dot to device. But it's already to device, right? So you have 10 data inputs the label and have data 0 to device, data 1 to device. Okay. So if it doesn't work, let's change the input a little bit. So for the torch data set, I can create uh, the data loader. So hopefully the data loader will help. So let's see if I can create the train loader, right, to be the torch utility. So I want to have the loader for this one, right? And when you have the loader in my loop here, right? So instead of I enumerate, I will use the data loader. So I would say for image label, right? For images label in the train loader, right? I can have image to device and label to device. And then this is not input anymore. It's going to be image to go to the model, right? And then we have the same label. Okay, let's try this one first. Let's comment out this one and then see if it's still giving me an error. So it does go through. Okay, so basically we change it to the loader to make sure that the data is loaded onto the GPU before we can actually perform everything on GPU. Okay, so we know that it worked, so we're going to stop it. And then we are going to change this one to be the same structure as this. So here I have to change this one to be for images and label in test loader, right? And then I have images and label two device, right? I can make it two device. And the output here is going to be from images, right? Which is the input, and then the rest will be the same. Okay. So we're going to try. It's going to take a little bit of time, I think, for each iteration. I'm not sure how many images are there. I haven't looked, but if you can see the cursor. So right now it actually go to each image, like get the model. Let's see if we finish one epoch very soon. So why is being trained? Um, so this is how you would do the CNN. Um, so first set have no attribute data set. Oh yeah, I have to change this one as well. So it's no longer trained data. It's the well the length of the trained data, and the test accuracy is also there's no data set, right? So uh it had to be the length of the train loader, I think. And then for the accuracy, so we have to compute the total as well. Okay. So inside here, we should have total equal to, so we have, so it should be plus equal to the label of size, right? So the correct, you sum to all the item to compute the size. Uh, Probably, I think it's the same, right? So I don't have to do the total. I just use the length of the 10 loader, hopefully. Okay. So what is running? Um, if you want to do the plot, you only have uh this list. Where's the list? This list that you can plot against the epoch. I'm going to wait until that, but we are going to do a little bit of the semi-supervised learning. So we want to use a mix match algorithm for semi-supervised learning. So we use the same data set, but we just pretend that part of the data set is not uh, the part of the data set is not labeled. So we split test train data set into label and unlabeled. Oh, unlabeled. Right? So we have so label train equal to uh, let's see, how can we do the split? So we are going to use subset, right? So subset is a library in PyTorch. So I say from Torch, oops, why does it go up? From Torch dot utils dot data import subset. So it's basically we do the subset of the data. So we have the subset of the train data, right? And then we have the unlabeled data train to be another subset. Now, in the train subset, we can actually specify the number. So sometimes we can pick the indices. So right now it will pick um, from 0 to 10,000, but we can uh, try a different label. So we can do uh, the random shuffle, right? So we can pick, let's say, the number of label to be, let's say, 4,000. And then, oops, number label to be 1,000. So, okay, so they are training, right? The train loss should go down. The test loss go down a little bit. Okay. So we have the number of label. We will create the indices, right? The indices is going to be the list of the length of the data load, the train loader, or the train data actually, right? So we have train data, we have train loader, right? Okay, let's try to make sure that I get the correct data set. So I will try again. So data set equal to torch vision, right? From the test, and then test data set equal to again torch the same as above, but the train to be false. Okay. All right. So we have the indices. So this one will be the train of the data set. All right. So the entire data set is the train. We will create a list of all the indices, and then we will shuffle, random shuffle the indices, right? And then we're gonna have the indices for the label and for the unlabeled. Oh, okay. Like so for the first 4,000, it's become the label, and then the the rest would be unlabeled, right? And then I have to import random, I think. Okay. So I load the data, I get 4,000 to be labeled, and then the rest would be unlabeled. And then I can say the label dataset to be the subset of the dataset given the label. the label as well. And then I can, so now that I have the data set, I can create the loader for it. Oh, actually, I don't have to. Okay. So for the first step in the mixed match, right? You want to do the cell train. So I will define the function that will generate the pseudo label, right? So the function, the pseudo label, and the parameter for the pseudo label, you have to send the model, right? You have to send the model. You have the unlabeled data, unlabeled, and then maybe the loader, perhaps, and then we have the threshold like that. So need, I need to create the unlabeled loader, I guess. Oh, but I can create that later. Okay. So I want to generate the pseudo label for all the unlabeled data based on the model, right? So I would have to say model.eval to make sure that I'm in the evaluation mode. I will have the pseudo set, pseudo label data to be empty, and then pseudo label, just the label to be empty, and then with torch dot no gradient, right? And then I have to go to each image. So for input, um, and normally there's no target because it's unlabeled. So I can say for input and then dash. So dash means that there's supposed to be a label, but we don't use it because we treat it as a label. And then we say input equal to input dot to device. And then output to be equal to the model. And then you put in the input. So once you have that, you can compute the probability, right? So f dot submax, you can use submax on the output with the dimension equal to 1. And then you take the maximum, right? So the maximum probability and then the prediction to be equal to the max, right? So this one will do the hard assignment, right? To be close to the hard assignment, right? So this the probability from the model. This one you take the maximum to be whatever it is, and then the prediction that gives you the maximum, basically. And then what you have is you have pseudo label data dot extend, right? Input I don't think it's CPU. I see, but I think it's okay. So input dot CPU not numpy, and then extend the prediction, change it to CPU. So Up until now, everything is on GPU, but when you want to save the data, it had to be on the CPU. So we convert the data into the CPU mode, and then convert it to NumPy, and then we extend it into the label data. Right. So basically, we add pseudo label to a label data. And then we also add the prediction as well. Right. So once we have this, so if we want to use the same model, so we can use again device equal to torch dot device, and then it should have QDAR, and then I create the model again. So I create a new model for semi-supervised learning. And then again, I can just copy the optimizer from this one. Basically, we use the same criterion and also optimizer. Right. And then we have the label. So we have the label loader equal to, so I should have the data loader on the top. So it's this one, right? So I copy it here. Right. So this one will be for the label dataset and unlabeled dataset, right? So I create a data loader, and then I train. So this one I would have to train the model from the label data. So this one is actually the same that we have, right? Basically the same structure code as when we train just normally, because we have the label. So I'm gonna go to very quickly. So for ePOS in range 20, maybe just 10. We have model.train. I will tell the model that I'm in training mode. And then for input and the label in the label loader, right? I do the same thing. And then loss backward optimization step. And once I finish, right? Once I finish training the label, I get the model from the training, from the label data. I can pass it here. I pass the model here to generate a pseudo label. Right. So that is the first step, right, of this one. Right. The first step of the mismatch. Right. You have label, and then you have the non-label. So the label here, you just train the train the model normally, and then for the pseudo label, you pass the model and then the unlabeled data, and then you get the label for the pseudo label. Right. And then you can try to do the mix match. I will do that next time because we are around 1 hour of time. We will go back. Basically, this one will be to be continued. So here, so it's not finished yet, but it should finish soon in like 3 epochs. So how long that is already trained? That is show the time. So like 15 minutes. So it's basically about 1 minute per epoch. Right. So you can use this one, the train loss, test loss, train accuracy, test accuracy to plot your graph. Right. So normally when you use neural network, These are the four graphs that you have to plot. When you write a report or when you want to publish a paper, people would look at this four plot, right? Plot the training loss based on each epoch that you train. Normally you go for like 100 or 1,000 epoch, but this one is for quick. So um, if you want to report the result, like consider plotting the above four values. So that's it for today. We will continue with the semi-supervised learning because there are a lot of work that you have to do. There is no one live code that will do everything for you because semi-supervised learning is like really customized method. All right. I also post the fourth assignment. You can take a look early. Next week, we will learn about reinforcement learning, which will be the main topic for the assignment 4. And then the week after, we will have a workshop about the reinforcement learning. Basically, we will try different things in the assignment 4. So to help you get started, because there are a lot of information in the assignment 4 and actually take a lot of setup to actually have it running. So I will have a class dedicated to help you set up. And then the week afterward, it's going to be federate running, and then we have a week off, and then we have the final exam. So I update the syllabus on the Mango Canvas website, so you can check the update of the schedule. Okay, if there's no more question, then I will see you next week. Thank you.